first thing we're going to talk about is the relationship between differentiability and continuity. So okay, now let's look at this first example that's on the sheet, okay, which is this absolute value function. So let's say f of x equals x squared minus 4, okay? And the graph is given there, but just a quick sketch, it kind of looks like that, roughly. Okay, and what we want to understand is this thing continuous? From the graph, is that obvious? Yeah, okay. And so what's the intuitive notion of continuity? Right, so like what does the continuity mean without getting all technical? Okay, and those both equal the value of the function at that point. Okay, so remember continuity's definition was that the limit of the function at a point equaled the value of the function at that point. The intuitive definition that you guys all remember from high school, right, was you can draw it without picking up your pencil, right, that thing? Okay, so this function certainly is continuous. Is it differentiable or not? Okay, so where might be the problem points that we have to worry about potentially for this guy? And let me label my graph. Oops. Okay, where it looks like there's problems? 2 and minus 2? Seem reasonable that there's issues there? Okay, and now geometrically or non-technical, why does it look like it's not differentiable at 2, for example? Okay, so what's sort of a non-technical definition for what it would mean to be differentiable? Right, what's the derivative all about anyway? Huh? Slopes of tangent lines. Okay, at the point 2, what's the issue with the tangent lines? I can draw a bunch of them with different slopes that only go through that point, right? There's just 2 examples. So it's not a unique value, and hence we have a problem. Okay, let's look at from the mathematical. He lives. New sheet, by the way. Let's look at from the mathematical standpoint why it's not going to be differentiable at the point 2. Okay, so in order to do that, we first have to remember what is the definition of the derivative. That, right? Okay, and that's going to be at the point x, whatever that is. We are interested in this particular function at the point 2. Okay, so in order to do that, I also need to first rewrite okay, what does the absolute value mean? Okay, well, what does the absolute value function do? If the thing you put inside of it is positive or 0, what happens? You just get that exact value out, right? If the thing that you put inside is negative, then you basically just chop off the minus sign. And what's a way to chop off the minus sign? If you have a negative quantity, could you just throw an extra negative in front of it? Right, because what, 2 negatives make a positive last time I checked? Yeah? Okay, so that's the specific definition of our function without using the absolute value symbol, okay? And the reason that I need to resort to that is because, well, this is a piecewise function, okay? So let me rewrite this slightly because, and sorry, this is a little disorganized. When is this statement the case? When is it true that x squared minus 4 is greater than 0? For which values of x is that true? Huh? 2, certainly. Minus 2 also. But also values that are bigger than 2 and less than minus 2, right? Yes? Okay, so this is true if x is in minus infinity up to minus 2 and then 2 to infinity. Okay, so first off, do you guys remember the interval notation from high school where the roundy parentheses and the brackets and stuff? Okay, what's the little u in the middle stand for? Union, and it just means that it's those two sets collectively together. Okay, and then what was the difference between roundy parentheses and brackets? Because I've got brackets on 2 and minus 2. Why are those brackets and not parentheses? Yeah, the number is actually in the set, okay? Whereas for this side, it's roundy, okay? So the roundy parentheses correspond to strict inequalities, meaning like less than or greater than, whereas the brackets correspond to less than or equal or greater than or equal, right? Okay, so you see the distinction? Good? Okay, so what I want, the reason I need to go into more specificity as to what f actually is because I want to compute the derivative of it at 2, which means I need to take this statement and just replace x with the value 2, and then compute those limits. Okay, sound good? All right, so I need to compute f prime of 2. This would be the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. Okay, but we have an issue here, and it's right there. What values could h take on? Now, h is going to 0, okay, but in our mind, like what sort of values of h would be approaching 0? Could h be positive? Could h be negative? Both possibilities are okay, right? So if h is positive, then 2 plus h is bigger than 2, right? Which means which line of the function is in charge? This one, because the input value is bigger than 2. But if h is negative, then 2 plus h is a little bit smaller than 2. So who's in charge then? This part of the function. Okay, so what do I have to do if I want to take this limit where the function has two different definitions on one side and on the other? I need to split this limit into two one-sided limits. So I need to do this limit, one version as h goes to 0 from the right, and a different one as h goes to 0 from the left. Okay, so because remember, what we're trying to figure out is if the limit exists, and when does the limit exist? If the left hand and the right hand version equal each other. Yes? Okay, so I just need to compute that. Okay, so let's do the left hand, the left hand version. Okay, what is f of 2 plus h? Well, I need to replace the x with 2 plus h. Which line of the function do I need to replace it in? The bottom one or the top one? the bottom one, because if h is going to 0 from the left, 2 plus h is slightly less than 2. Yes, which means it's the bottom line of the function. Good? Okay, so I'm going to replace here, oops, 4 minus 2 plus h squared, right? Because what's the function? 4 minus x squared. Yes? Okay, then I need to subtract f of 2. And what is f of 2? That should be pretty quick. It's 0. Okay, so that's really convenient just because it'll make the arithmetic easy. Okay, we get that. All right, any questions up to that setup point? No? Good? Okay. So what do we need to do next? Can we just FOIL everything out and start to simplify? Okay, and let's not screw up the foiling. All right, so what's going to happen with the 4s? Yeah, they cancel. And so I've got minus 4h minus h squared over h. What happens to an h? Cancels. And so I just get minus 4 minus h. And what's that limit? Negative 4? Yeah? Okay, good. Okay, now, I just did the left-handed limit, and I got minus 4. Great. What do we need to do next? The right-handed limit. Okay, and so here I need to compute the same definition, except who's in charge this time? Yeah, the other version. So it'll be 2 plus h squared minus 4 minus 0 all over h. And now we just need to do the same thing. What's going to happen when I FOIL it out? The 4's cancel. The h's cancel. And so I get what? 4 instead of minus 4. Okay. And that kind of makes sense because the function is just flipped basically for the other part of its domain. Okay. So what values did I get? I got 4 and minus 4. Are those the same thing? No. Okay. So what is the conclusion? The limit fails to exist. But what did the limit define? So what was the limit here? It was this guy. Okay, so that limit failed to exist because the left-handed and right-handed version disagreed, but that limit is the definition of the derivative. Okay, so what does this mean at the point 2? The derivative doesn't exist. Okay, and so the function's not differentiable there. Okay, now if I had done this exact same argument at 3 instead of 2, would it have worked? Yeah, it would have. Okay, the two limits would have come out the same. And in fact, they would come out the same at every point except 2, which we just did, and also 0 is okay, at negative 2, okay? Because those were our two weird points, and maybe you can sort of expect why that ought to be the case, because where was the border between where we had our two definitions of the function? Where were the transition points? 2 and negative 2, right? So those are automatically going to be the places that are sus, and then we have to go through the limit to determine that, yes, in fact, we want to throw both of them out the airlock. Yeah. See what I did there? Yeah, making video game references. Yeah. Okay, good. Okay, so just because a function is continuous at a point doesn't mean that it's differentiable at a point. Okay, and we've just found an example, there's crap tons of them, of a function that's continuous but not differentiable. Okay, make sense? So what about the flip question? I just figured out a function that's continuous but not differentiable. Do you think it's possible for me to come up with a function that's differentiable but not continuous? Hmm? So you're shaking your head. Is it possible or no? Right, so I want a function that's differentiable but not continuous at a point. Okay, let's think about what that would look like. What does differentiable at a point mean? It means you can draw a tangent line uniquely. Okay? Continuous at a point means that there's no breaks or jumps or weird holes or something like that going on. So just thinking about the drawing pictures, do you think it's possible? Okay, well, let's determine. You think it's possible? Ah, sorry, Bucko, but you're wrong. Okay, it's not possible. In fact, we can prove it. Yay. So, how many of you guys, when the word proof came into math, you were like, this is the worst day ever? It wasn't that bad? Was it more bad or less bad than the day that the alphabet got involved in math class? More bad? Worse? Okay. Because when the alphabet got involved in math class was when I actually started liking math. I was like, wow, this is really cool, right? Because what was math up until that? Well, arithmetic. And you know what I really sucked at doing? Tedious arithmetic. So, anyway, actually, when I probably should have known I was going to be destined to be a mathematician because I remember, oh, it's sometime in probably middle school. In math, we were factoring polynomials, and in English, we were diagramming sentences. And I had this epiphany that, hey, these are actually the same sort of thing. Yeah. Okay. All right. Anyway, so it is not possible to have a function that's differentiable but not continuous. Okay. Here's the proof. Okay. In order to prove this, I need to make one slight redefinition of what the derivative is defined to be. Okay. Okay, so this is another way to define the derivative at a point. Okay, and in some sense, actually, this one is maybe a little easier to see why it's the definition of the derivative, because what does the fraction look like? Sure looks like a rise over run computation to me, right? And what is the derivative? It's a slope, so it's a rise over run kind of thing. Yeah? Okay, so this is a slightly different looking definition than the one involving h, but it's equivalent to it. Okay, so they both actually, if you were to compute this for a function, you get the exact same thing if it's differentiable. Okay, So I'm going to use this version of it. Okay, now, what is it that I want to show? Okay, that's what we want to show, right? That f is continuous at A. What does it mean for f to be continuous at A, at a point? No holes, no jumps, no none of that business, okay? What does it mean with limits that that function is continuous? And they have to equal the value of the function, right? So what is the definition would then be that is that the limit as x goes to a of f of x equals f of a. Okay, we need to show that the limit equals the value of the function. Now, the limit can only exist under what conditions? The left and the right-hand versions have to be the same. Yes? Okay. And, damn it, the value of the function, well, I can't write this down unless like I can actually plug a in the function, right? So the function's got to be defined at the point for us to do anything. Okay. So the f of a existing means there's no hole, or sorry, f of a existing means there's a dot. The limit existing means there's a hole but not an asymptote. And the two things being equal means the dot is in the hole, meaning you didn't have to pick up your pencil. Okay, yeah? Okay, so that's what I want to show. Okay, so let me take here, what I'm going to do, what's an equivalent way to show that those two things are equal? Okay, so what if I took that equation and rearranged it slightly? What's another way I could write it? Yeah, I could subtract them. And what should I get if I subtract? I should get 0. Okay? We? Okay. So, and that is the worst looking A I've ever written in my life. Okay, so I want to show that that difference is equal to 0. Okay, now why do you think I wrote it as f of x minus f of a? I didn't just pick that out of thin air. What do you think maybe motivated me to make that move? Okay, which was kind of the same trick in the Monk problem, right? But the other reason I did it is because what do I know something about? I know something about the derivative, and f of x minus f of a appears in the derivative, right? So that looks similar to something I have, okay? All right, so I want to compute this limit. Oops, I'm sorry, not h. Damn it. Sorry. All right, I want to compute the limit as, okay, let's just try this again. Limit as x approaches a of f of x minus f of a. Okay, and I claim that this is equal to 0. If I show that this is equal to 0, then I have shown that the function is continuous, and we're Gucci. Okay, but I don't know it's equal to 0 yet. That's just what I want. Okay, so can I do the following? Oops. Here, let me clean this up slightly. Is that the same thing? Okay, why? Because what happens to the x minus a's there? They cancel, okay? So what I just did was multiplied by a disguised form of the number 1, right? So I haven't actually changed anything. I've just changed how it looks. Okay, now, what is true about, I've got a thing in parentheses and a thing in brackets, and I'm multiplying them, and then I'm taking the limit of them. Well, what's the true about the limit of a product? Is it the same as the product of the limits? Yes. So I can split this up into this times this. Okay, I can only do that provided that both of these limits exist. Okay, now, do both of these limits exist? Let's argue why that's true. Well, what's this first limit? As x goes to a, what does x minus a go to? 0. That definitely exists. Okay, so, excuse me, the first limit is 0. What is the second limit? Does it exist? Now that's a little harder to see. Does it exist? Well, okay, if you just plug a equal to x in, what do you get? You get 0 over 0, which is a problem, okay? But let's think about, what does this limit represent? This limit was another way of defining f prime of a, right? Do we know that f prime of a exists for this function? Yes, because that was the hypothesis, that it was differentiable. Okay, so what that means is this is equal to 0 times f prime of a. Well, last time I checked, what's anything times 0? QED. Have any of you guys ever seen QED before? Nope? Okay. So, time for your liberal arts college lesson of the day. That stands for Quod erat demonstrandum. Oh, it's so much clearer now, isn't it? Huh? Actually, it probably is. If you looked up QED, you'd probably see a definition. Okay. So, quod erat demonstrandum is a Latin phrase, which means that's what we wanted to show, or the very, basically we've proven what we set out to prove. It is the Latin translation of this Greek phrase, okay, which that one I can translate much better for you. Ha is a relative pronoun, okay, so the thing which, if you put pair at the end of something, it intensifies it, so it's the very thing which. Ede, de, it was necessary. Ede, or sorry, it is necessary. Ede, it was necessary. The very thing which it was necessary, deixai, to prove. Because I know Greek and my Latin is really rusty. Right? So, ha pair, relative pronoun, or pair is the intensifying part. De is it was bind, or it is binding that. And then that takes an infinitive, which is deixai. That's the aorist infinitive of deignomy, which means to prove or demonstrate or show. Yeah. So, no? You guys all aren't up on your Latin and your Greek? This is intolerable. They're all letters with a breathing mark and acute accent, a a non-breathing mark and acute accent, and this is a circumflex. So, yeah. Where's my coffee? Balloon? What? This? This? Oh, that's a C. C. Right? The capital is sort of a TIE fighter looking thing. Yeah. So that's it's called a double consonant, but it basically is the ks sound. So it's like KS in English. Okay. So, and in fact, you guys know words that came from Greek that have this. So in English, they tend to have an X because that's what makes that sound in English. Helix is a good example. Um, that's a Greek word, right? What's another one that ends in an X like that? Well, in Greek, I'll give you one. Phulax. Okay, it means guard, from which we get the word prophylactic. You guys know what a prophylactic is? Is anybody going to have a young lady come over or a young man come over tonight? Definitely not here. Get frisky. Well, you might want to use a prophylactic if you were. Okay, so it literally means a guard on the front, and I'll leave it up to your imagination where how to take that. Okay. Um, anyway, so we just proved what we wanted to prove. All right, so let's talk about the mean value theorem. Okay, so we've seen that it's possible for a function to be continuous and not differentiable, but not vice versa. If the function's differentiable, then it must be continuous. Okay, so let's suppose that we have a function that's continuous on an entire interval of points, because we also saw that continuity could be true at one place and false someplace else. Right? Same thing with differentiability. It was possible for everything to be cool one place, but not cool in another. Okay, so suppose that those things are true, that we're continuous on a closed interval, and we're differentiable on everybody inside that interval. Okay, and we're not going to worry about the differentiability at the endpoints for kind of technical reasons. Okay, then sorry, my handwriting is terrible this morning. Okay, now I just made this statement. What the hell does it actually mean? Right? Okay, so what is this quantity f of b minus f of a all over b minus a? What does that remind you of? What does it look like? Kind of looks like the derivative, but it's not because there's no limit there. Okay, but does it look like a rise over run computation? Yeah, okay. So let me draw an example curve. Okay, and let me say that this is a f of a, and this point up here is b f of b. Okay, can I connect those with a straight line? Okay, and using the magic of the iPad, I actually get a pretty decent looking straight line. Okay, I would like to know what the slope of that line is, please. Exactly, right? What is the slope of a line? It's rise over run. Well, what's the rise? F of B minus F of A. And what's the run? B minus A. Okay, so what is that straight line called? We just computed slope. It's called a secant, yeah? Okay, because it cuts the curve in two places, whereas opposed to a tangent that touches at a single point. Okay, and so the slope of the tangent line is that, f of b minus f of a all over b minus a. Okay, now, what this theorem is saying is that assuming the hypotheses are true, there is a place where the derivative equals this slope. So looking at my graph, do you see a place where the tangent line would have the same slope as this secant line? What does it mean to be same slope, by the way? What's another way of saying that? Parallel, right? So is there a place where you can draw a tangent line that's parallel to that secant line? Yeah, okay, where is it? Yeah, it's roughly in the middle just because of the way I drew the graph. It doesn't have to be exactly in the middle, but it might be somewhere kind of like, roughly there. Does that seem plausible? Okay, so this point is at C, f of C. It's somewhere in between A and B. There's a place where the tangent slope is equal to the secant slope. Okay, so that's geometrically what this thing is saying. Now, does it tell us where exactly the point is, the point C is? No, it just says that there's somewhere between A and B where this happens. Does that remind you guys of another theorem? Yeah, I mean, it's like the intermediate value theorem, right? The intermediate value theorem gave you the existence of a point. It said it's somewhere in here, but it didn't tell you any more detail about that. So if you wanted to find such a point with the intermediate value theorem, we had to do things like the bisection method or just kind of look at graphs and things like that. Kind of same thing here, okay? Um, or maybe do some algebra or something, okay? So this is another example of an existence theorem. It said a thing is there to be found, but it says nothing about how to go about and find it, okay? All right, so let's use a real world example for this, okay? Let's suppose, so I'm driving to Butler today. Okay, and let's suppose that it's exactly 60 miles from here to Butler. Okay, and I'm just picking. I mean, it's 60 miles is not actually that far off, but let's just say that. Suppose it takes me exactly 1 hour to get there. Okay, what can you conclude about this? Okay, so you laughed when you said that because, of course, that's not true, right? So you said, all right, if I went 60 miles in an hour, then my average speed was 60 miles an hour. Okay, does that mean that my speedometer actually was at 60 miles an hour for the entire trip? Not necessarily. Could be. Now, is it that likely to be the case for my actual drive to Butler? No, because when I'm here in town, I'm going to be going like 30 or 40, and then I'll get out on the interstate and be going like 70, 75, right? And they're going to average out to being about or to 60, okay? However, is there a point in time when my speedometer does read 60 miles an hour? Yes. It just may not be the whole trip. It could be, right? So for example, let's say that I was on like a freeway in the middle of nowhere in Kansas and I got the cruise control on. Well, maybe I would go exactly the same speed the whole time, right? It's not likely in a reasonable driving scenario, but it's at least mathematically possible. Okay, so what the mean value theorem says in this situation, well, okay, first off, is it reasonable to assume that my drive to Butler is a continuous function? Okay, because what would it mean for it to not be continuous? Yeah, I don't have a teleporter. The physics department has been slacking, okay, on their duties. Okay, so I don't have a teleporter. I also don't have a fusion reactor, right? Or flying car. Like, what's up with the physics department? They need to get with the program here. Okay, so it's reasonable to assume that my drive is continuous. Is it reasonable to assume that my drive is differentiable? Okay, reasonably so, yes. Because what would it mean for my drive to not be differentiable? That's called crashing somewhere and having a sudden, instantaneous change in velocity. That's weird. Okay, that's called crashing. Let's hope that I don't do that. Okay, so reasonable to make those assumptions. So, like I said, the average speed is 60 miles an hour, right? And you could have done this computation back in elementary or middle school, right? So where's the calculus here? The calculus says that not only is the average speed 60 miles an hour, but there is at least one instant in time along my drive where my speedometer reads precisely 60. Okay. Now let's kind of think about it. How many places do you think there will be for which that's true on my drive to Butler? Probably at 2 places. As I accelerate onto the highway, I'd be going from like 40, 50 up to 75. So would I have to go through 60 to get there? Yeah, okay. That's kind of intermediate value theorem thinking. And then similarly, when I get off the interstate close to Indianapolis and I'm then back on side streets, then I'm going to go from being at 75, or well, actually, it'll happen when I hit between Brownsburg and whatever, right, where the speed limit drops, right? But point being, there's a second place where I'm slowing down and going through 60 from a higher speed to a lower speed. Does that seem reasonable? Okay. Now, here's a question I've always wanted to know the answer to. How many of you guys are from like Chicago area? All right. So, in Chicago, how many of you guys have easy passes? Yeah. So, where could the mean value theorem be really useful if you were the people who run the tollways and the easy pass companies? Well, let's say that you go through one toll plaza and then you get scanned and then you go through the next one and they compute your average speed, and let's say that the speed limit along that stretch is 70 miles an hour, but they calculate your average velocity to be 90 miles an hour. What can they conclude? You were definitely speeding. And in fact, there was a point where your speedometer read exactly 90, right? So what I've always wanted to know is if the tollway authorities use the mean value theorem to issue tickets. They could, but I've never heard of them doing it. Okay, now, the reason I still don't know the answer to this question is because what would get me the answer to that question would be a letter to them and or a Freedom of Information Act request. But I don't want to give them the idea if they don't already know it, right? So, yeah. Okay. So, huh? Does he work for? Okay. Yeah. Yeah. Ask your dad. That's your assignment this weekend to ask your dad. So, Dad, do you use the mean value theorem to bust speeders? And he'll be like, "What the hell are you learning at this? How much am I paying for you to learn all this crap?" Right. So, yes. Anyway. Okay. So, mean value theorem. Um, we didn't get through quite as much as I wanted, but the um, that's okay. Why don't we just continue with this next time? So what I'd like you guys to do for Monday is think about the first two questions here on page 2, okay, about this elevator ride and the hot chocolate question. Okay, think about those in the context of the mean value theorem, and then we'll pick up with this on Monday. Yes, it's past my cutoff time, and now I need to go get the things to hand back to you. Okay? All right. Have a good weekend, guys.